Okay, with Emilio on board, I guess we can start. Welcome everyone to this week Autonomy Talks. This week is a great pleasure to have with us Dr. Sumeet Singh, who is a research scientist with Google Brain Robotics in New York City. You can tell that he made the upgrade from academia to industry because you see these fancy colors, these fancy colors in the slides. So something about Sumeet. He completed his PhD at the Autonomous Systems Lab at Stanford with Marco Pavone. And for his PhD, he got some fellowships and some awards, among which we note the Stanford Graduate Fellowship, the Qualcomm Innovation Fellowship, and the Best PhD Thesis Award from the Department of Aeronautics and Astronautics. Sumeet's current research interests include efficient and robust motion planning for constrained robotic systems, and also is well known for leveraging nonlinear control theory for the design of learning-based controllers and algorithms. And today's topic will be exactly focusing on this part, and it's going to show us how contraction theory can be helpful to design constrained optimization problems for learning controlled dynamics models with applications to planning and control. Of course, this has clear connections to what we are interested into in the Autonomy Talks series. And that's why I'm very excited to hear the talk. So without further ado, Sumeet, the stage is yours.
Well, great. Thank you so much for having me, and thank you for the introduction. I actually can't see the Zoom screen, so I'll periodically pause for questions as we go along. So welcome, everyone. The topic for today is on trying to come up with ideas of how to embed control theoretic structures within learning algorithms. So I'll start out broad. And in recent years, we've seen a proliferation of these large language models and large language and vision combined models. And so far, it suggests that we haven't quite hit the limit of scale on these models. And in fact, as we keep increasing the number of parameters, we're seeing improved performance in a variety of different tasks associated with these models. This is translated also into the vision domain, where we can now generate quite incredible looking images. I think this is the one that stood out for me, where it's now combining different modalities, including language and vision. And more recently, there was work that just came out from the robotics group at Brain, which essentially takes a pre-trained language model and gives it the task. Let's say I spill my drink, can you help me figure this out? And the language model basically gives you a set of subtasks that it thinks are most relevant in the situation. And then this is combined with a value function that's trained based on different types of policies with these subtasks. Together, they're combined to essentially rank in which order do you want to listen to the subtasks being generated from the language model. And I think this is quite incredible, and I'll come back to this idea later on at the end of the talk. This is quite incredible because it suggests that we can use some of these pre-trained language models to tackle one of the hardest challenges in planning and control, which is the task planning aspect of things. But despite all of these advancements in these large language models, I still believe that the low-level control problem, which involves manipulation, dealing with non-smoothness and doing agile control, doing uncertainty quantification, how to deal with multiscale, multi-frequency sensor fusion, and then also dealing with the inherent multimodality that certain tasks still have. I think these problems are still quite challenging for control. And therefore, the overall problem is still not very solved. And so the idea of my research is to try and incorporate the natural control theoretic structures that appear in these problems within the learning-based algorithms that we design. So what do I mean exactly by these structures? So some examples include ideas such as stability and stabilizability whenever dynamical systems are involved. Exactly addressing how to handle robustness to both model and estimation uncertainty. How do we make corrections both to the model and to our policies based on sensitivity analysis? How do we come up with operators that operate directly on time series and generate functional transforms as opposed to thinking about things in a discrete MDP way? How do we encode various types of geometric biases, for instance, rotational invariances, nerf type encodings? How do we build these invariances into these models and policies? And finally, how do we associate constraint handling into these problems? So a lot of the time, deep RL algorithms ignore the fact that there are severe problem constraints and limitation constraints on actuators and on the state space. How do we actually incorporate these in a principled way that's still differentiable so it's amenable to higher level learning algorithms? So, and of course, there are a lot of other ways to incorporate control theoretic structures into these algorithms. The topic of today's talk, however, will focus on two specific sub-themes here. So the first is on stability and stabilizability, where I'll show in a model-based RL context how we can use the ideas of stabilizability derived from nonlinear control and embed them within model learning algorithms that can dramatically improve our sample efficiency. And then the second part of the talk on more recent work, I'll discuss this idea of functional transforms and operators on time series that allow us to seamlessly integrate multiscale, multi-frequency sensors. And in this work, this is done in context of imitation learning, but really it's more, the idea is really more on an architectural scale so that it can really be applied to various types of learning methodologies, including model-based RL, deep RL, or anything else that you'd like to use. I'd also like to mention an additional example, just from the original list of these type of control theory structures, on how we can use notion of sensitivity-based analysis and differentiating through optimization problems to speed up classical robotics algorithms such as trajectory optimization. So I'll just point you to a link on that work, but I won't go into any detail on that. So we'll start off with the first part of the talk on stabilizability within model-based RL. So the outline, I'll first motivate why we need notions such as stabilizability. And this will motivate using a tool known as contraction theory. And I'll go into some of the fundamentals of contraction. And then finally, how it's being used in the context of model-based planning, and then how it can be incorporated into model-based RL and associated experiments. So the standard setting of model-based RL starts with this following process. You observe some trajectories on your system. You record tuples of the experience, such as state, control, state derivative, or next state. You try and fit a model to this experience, and then you use this model to generate new trajectories or new rollouts. And this can be done in two different ways. Either you can put this as part of a model-based policy optimization algorithm, or you directly use this model to generate new trajectories in a motion planning context. And the overarching, I think, theme in model-based RL compared to model-free has been that model-based fails to keep up with model-free methods, especially as you increase the number of samples. And our hypothesis here is that one of the fundamental reasons why this happens is because there is no guarantee on the learned dynamics model, no guarantee on the learned dynamics model that the trajectories that you will generate with this model will be followable, or will they be controllable, or will they even be stabilizable with a feedback controller. And the same holds on the policy optimization side of things, where you have no idea if the rollouts from your model are actually stable inherently. And I think this is a fundamental limitation in most model-based RL algorithms. So the way this is typically handled in the literature is that, of course, a naive approach is just to try and treat dynamics learning as a pure regression problem. But as we know, this leads to divergence after a few steps, and therefore there's several works that try and augment the data with corrections to try and incorporate multi-step losses. You can take an uncertainty angle on this by trying creating probabilistic models such as Gaussian processes and apply stochastic control. But usually what this results in is overly conservative algorithms where you want to, for instance, guarantee the invariance of a safe set. And this usually results in a very conservative control policy. There's also this hybrid algorithm of model-based, model-free, where you try and learn a model-based, you try and learn a dynamics model such that the policy optimized from that model will guide you optimally in the task that you care about. So you train it almost in an RL way. But in this case, the dynamics that you're learning may not capture anything about the underlying physics of the situation. It's simply just a representation that helps you do well with the induced policy derived from that model. And then finally, a little closer to what we're actually going for is the notion of imitation learning with stable dynamics, where you try and learn the dynamics in a stable encoding of the dynamics for just the output motion, but then you rely on the fact that the entire robot dynamics are actually invertible, so you can realize the joint motor commands to realize the desired, let's say, end effector motion. Naturally, of course, this approach doesn't scale to under-actuated systems. So the hypothesis in this first part of the talk is that naive model-based RL doesn't consider the stability implications of the downstream application. And the application here is planning and control. So what we would like to instead propose is a dynamics learning algorithm where we embed a constraint that the learned model is stabilizable. And the way to sort of think about this constraint is what you're doing is you're pruning your hypothesis space in a way that's tailored to your downstream task of planning and control. And so obviously the natural question is, how do we represent the stabilizability as a generic nonlinear constraint? So this is where we'll introduce contraction theory. And broadly, the idea of contraction theory is to go from talking about nonlinear stability on an infinitesimal scale. So really think about stability of nearby infinitesimal variations. And how do you take that notion and draw conclusions about stability on a finite scale? So between a pair of finitely apart pair of trajectories. So let's get into the basics of contraction. Let's say I give you a trajectory of a system, of a nonlinear system that satisfies this nonlinear control affine form. And now I want to talk about the dynamics of a virtual displacement that basically traverses along this trajectory. So we'll define delta x as a virtual state displacement and delta u as a virtual control displacement between two infinitesimally closed trajectories. So the correct interpretation of delta x and delta u are that these are tangent vectors that lie in the tangent space of your state and control manifolds. So we can write down the dynamics of this variation along this given state control trajectory. And this comes out to be the Jacobian linearization of your dynamics. And now what contraction says is, can you find me a positive definite matrix function M along with a differential controller, so a map that goes from state control and differential state variations to differential control variations, such that I can guarantee the time derivative of this quadratic Lyapunov thing is negative. So the picture that should be in your mind is we're talking about a Lyapunov function that is sort of swept along the trajectory, and it's measuring the size of these infinitesimal variations. So what you want is this differential controller to try and stabilize these differential variations along any given state control trajectory of your system. If we can find such a matrix M and an accompanying differential controller, then we call the matrix M a control contraction metric. And then the function V is known as a differential control Lyapunov function. So for those of you who are familiar with control Lyapunov functions, there's a very clear reason why we call this a differential CLF. Because if you think about the generic definition of a CLF, it says that if I give you a nonlinear system, let's say in control affine form, then the function V, a positive function V, is a CLF if which basically says that if control can do nothing to affect the time derivative of function V, which means grad V dot B equals 0, then the system must be naturally stable. And this is a sufficient condition to ensure that you can find a stabilizing controller for the system. In the exact same way, this is how the differential CLF is defined, which basically says if I write down the time derivative of my differential CLF, then the part that multiplies delta U, if that is equal to 0, which means delta U can do nothing to affect the time derivative of V, then the residual time derivative of my differential CLF must be stable by itself. And so we've gone from like the traditional bowl-like energy function that we think normally associated with Lyapunov functions around an equilibrium point to this swept infinite sort of parameter family of Lyapunov functions, of bowl-like functions swept along a state control trajectory. So at this point, we've established how to create the notion of stability on an infinitesimal scale. These are all with respect to tiny variations delta x. So how do we actually formalize this to draw conclusions about stability between a pair of finitely apart pair of trajectories? So the rest of contraction analysis, and I'm not going to go into too many details about how this proof is constructed, but the idea is basically this: you have a trajectory that you'd like to follow, which is x star of t in red, and then the trajectory that you're actually following on your system, which is x of t. And then what contraction says is consider the set of all the curves that connect x star of t to x of t, all smooth curves. Then I can quantify the length of these curves using this integral measure. And this is simply just the integral of my Lyapunov function along these curves. And this defines a notion of energy, or in this case, length, or in this case, what we call this as the energy of the curve. And what we want to do is find the curve, the shortest curve that connects x star of t to x of t. And this is known as the minimizing geodesic. And the minimizing energy is known as the Riemann energy. So now the rest of the contraction analysis basically says that if I can find a contraction metric m with which I've computed these lengths of curves and with which I know there exists this differential controller, then contraction allows us to prove that the Riemann energy, the time derivative of the Riemann energy, satisfies the same exponential decrease condition with respect to the same lambda contraction rate. And this is sort of the great result here, that what we started from is this notion of linearizing around any nominal trajectory and saying we can talk about stability on a linearized analysis method, but then we can actually, by way of integration, actually draw conclusions about stability between finitely apart pair of trajectories. So the question is, why would you want to do this? Why go through the effort of constructing these contraction metrics and this seemingly complicated notion of stability? So the first result is the fact that this Riemann energy is actually a control Lyapunov function between pairs of trajectories, meaning that if I want to derive a feedback controller, a feedback tracking controller from this actually becomes trivial. It is actually equivalent to just searching within the space, within just a half space, where the half space is parameterized by the dynamics at the desired point and the dynamics at the actual point and the connecting curve between these 2 points. So we get a very simplified feedback controller. Second, it gives you natural disturbance rejection properties. So if there's a disturbance acting on my system, one can show that if you're applying this CCM-derived feedback controller, we can ensure that our Riemann energy, this distance-like quantity, is always bounded, where the bound scales proportionally to the size of the disturbance and inversely proportional to how aggressive your controller is, so the lambda contraction rate. And this essentially means that along any given trajectory that I might have planned for my system, I can bound this trajectory with these Riemann energy balls and even overbound them with ellipsoids. And I can use this ellipsoid, let's say, as a collision margin when I'm doing tube-based motion planning. And finally, the third, and this is really the key benefit of this technique, is the fact that we can write down the conditions for the existence of a contraction metric as a set of algebraic properties. And these basically look like a set of equality constraints and a couple of linear matrix inequalities in the dual metric, meaning the inverse of M. So instead of actually searching for M, we actually search for the dual, which is W of X. So naturally, these are infinite dimensional constraints because we want these conditions to be satisfied everywhere in the state space. But because they're convex, we can apply various infinite dimensional reduction techniques, things like sum of squares programming and sampling-based methods to search for a metric. So as an example, this is where we applied this in a motion planning context, where we search for a metric offline. We do the computation of this metric-like function offline. And then online, we simply need to just derive the feedback controller associated with this metric, along with the pre-computed margins that come with the metric in terms of disturbance rejection. In this case, the disturbance here is drag. And we can use that collision tube margin for our motion planning algorithms. And then we have further results on much more aggressive flights as well. So I just want to pause here before we sort of move on to the learning aspect and see if there are any questions. Nope. Okay. So now that we know that we can write down stabilizability as a set of algebraic conditions, we can now go ahead and embed these into our dynamics learning algorithm and implement them as constraints. So basically, we want to say that replace that constraint of f being a stabilizable model with the fact that our control affine model, parameterized by the functions f hat and b hat, come with a control contraction matrix M of X. So now we can replace M with its dual and get a set of algebraic conditions in W. And so we get a joint optimization problem between the dynamics, F hat and B hat, as well as what is now known as the stability certificate, W. This is the thing that certifies that the model F hat and B hat is actually a stabilizable model. So naturally, now we have these infinite dimensional constraints, and in the learning context, the standard thing to do would be to sample these constraints. So it turns out, at least for the equality constraint, we can solve this exactly by simply imposing certain structural constraints on W. And for the inequality constraints, we can approximate these constraints by sampling. And the thing to note here is that we have two sets of sample sets. The top level sample set, which is what goes inside our objective function, is penalizing the regression error in our learned dynamics model. So this is the collected supervised data. And then the second data set are the set of points in the state space where we're imposing these stability inequality constraints. So this second set is completely independent, but it can include the regression set. And this is what gives us essentially a semi-supervised learning algorithm flavor. So some nice theoretical properties about this is that with this sampling-based setup, we can actually show if our function classes lie in an RKHS space, along with W as well, that we can prove a generalized representative theorem result, which states exactly what the form of the optimal solution for F hat, B hat, and W should look like, as essentially a summation of kernel terms, as a summation of kernel terms at the sample points. So naturally, now we do the natural thing associated with kernel methods, where if we don't obviously want to retain the solution that depends on every single sample point, so we use random matrix features to try and reduce the dimensionality here. And now what basically we get a biconvex iterative algorithm where we alternate between fitting the dynamics model, so minimizing the regression error subject to the inequality constraints with the current estimate of our stability certificate, and then fitting the stability certificate. So we fix the dynamics model and then iterate on the contraction metric itself. And then in the paper, we talk about various techniques on how to subsample the constraint set to make sure that these large optimization problems with these set of inequality constraints actually remains tractable to solve. So some quick results. So we validated this on a planar quadratic system where we generated varying data set sizes of tuples of state control state derivative, and we learned 3 different models. The first model is a pure least squares model with no regularization at all. The second model is where we apply standard L2 regularization. And then the final one is the CCM model, where we use approximately 2,500 extra constraint regularizing points that, once again, they were sampled independently of our demonstration data set. And then the task itself is you only get to observe this data set once, you only get to learn the dynamics once, and you must use the learned dynamics model to now generate and track new trajectories from random initial states to a stable hover condition at the origin. So I'll present some summarization results first. And in the realm of small data sets, when you only have about 100 data points, the thing to note here is that despite the fact that we only have 100 data points, the CCM model is able to generate high quality models such that when those dynamics models are used for planning and control and tracking, we're actually able to achieve good quality tracking. So what I'm presenting here is the RMS tracking error along the trajectory. In contrast, the models that use no regularization or the models that use L2 regularization still end up with these spurious aspects in the learned dynamics model that generate highly unstable trajectories that are impossible for the system to track. And then what essentially happens is that as we increase the number of samples, this difference between the CCM model and the unregularized models starts to shrink, which is what you would expect. As you collect more and more data, you should expect your learned dynamics model to essentially converge to a point where you can use it for planning and control. So once we reach 1,000 points, the standard L2 regularization model seems sufficient, even though the CCM model is still outperforming it, whereas the no regularization model can still generate highly unstable trajectories. We also validated this on the real platform, where we took a quadratic system, we implemented some partial closed loops to close the outer plane motion. And then we collected about 2 minutes of planar training trajectories. These included things like circles and sweep trajectories, and extracted just 150 samples of state control and state derivative. And then the task was to generate this figure-8 trajectory and then try and track it with just a time-varying LQR feedback controller. So this figure-8 is actually a set of 2 figure-8s where you start out at 0 velocity, you accelerate down through the middle, come back around, accelerate once again, and then decelerate at the final part of the figure eight back to a stable hover condition. And what we observed with the CCM model is just with 150 data points, we get a wonky looking figure eight, but at no point does the system actually crash. So this is roughly a figure eight, and I will create a snapshot at the end. It touches the floor at one point as well, doesn't crash, and still manages to come back to a stable hover condition. So it's kind of a figure eight. Whereas the L2 regularized model starts out okay and very quickly becomes unstable as soon as it gets to the higher velocity. And this was repeated over several trials of learning and deployment. So what's really been exciting is there's been a lot of follow-on progress on these ideas of encoding stabilizability and stability into the learned dynamics model. So I just want to mention some follow-on works here. For instance, there's been work on universal adaptive controllers that combine both CCM-based controllers and model-based adaptation. There's been works where instead of trying to learn a dynamics model, you directly try and learn the feedback controller, but then you regularize the entire closed loop system with the conditions derived from the CCM notions of stability. And there's also been a lot of great work on the theoretical side of things where one can ensure that you get improved generalization bounds when you're trying to learn stability certificates, so things like Lyapunov functions, from observed data, when you assume notions like incremental stability, where incremental stability is closely related to contractive stability. And some of the ways, I also want to mention some of the ways that we're currently extending this work, where the idea is that everything I presented to you so far assumes that our underlying dynamics that we're trying to learn is actually exponentially stabilizable. And this obviously could be a very strong assumption for certain class of systems. So we can easily, however, change this assumption to saying that instead of assuming that the underlying system is exponentially stabilizable, if you provide me with an expert who can control the system in a stable way, then that's the only dynamics I really care about. That closed loop system is the only system I care about. So the idea is, let's say I give you a data set of expert trajectories that are stable. So what we want to do is encode these. Again, it doesn't matter if it's continuous time or discrete time, we can derive analogous conditions here. We want to encode these trajectories as a dynamical system where the system is imposed to be contractively stable. And of course, this obviously relies on the fact that the expert demonstrations are themselves stable. Then step 2 of the algorithm says that we want to do policy optimization, but with a composite loss. So we have our objective that comes from the task itself. And then we have a secondary cost, which is a tracking-based loss. And the way to think about this is as following. We have a rollout from our policy through the system. Then at every point, every state sample along this rollout, we can create hypothetical rollouts from the learned dynamical system, which is G, which is stable. And what we want to do is impose a tracking loss between these hypothetical rollouts from a stable system and the actual policy rollout. And you can think of intuitively why this is a good thing to do, because when we talk about the natural issue with distribution shift, the distribution shift is really the divergence of the policy rollout from the expert trajectories. So you can think of it as breaking this down into 2 terms in a triangle inequality, where this is composed of the divergence of the learned dynamical system G from the training data. And this we can now bound easily using the contractive properties of the system. And then the second aspect is the divergence of the policy rollout from this learned dynamical system, which we explicitly minimize in our composite loss. And therefore, we can also bound using generalization analysis. And so this essentially gives you, using a triangle inequality method of analysis, it gives you a tractable way to bound the performance of your policy under a distribution shift. And it additionally allows you to bound exactly how much you can expect your policy to deviate from the expert data manifold. So this is currently ongoing work, but we've managed to validate this on some systems. So here's an example where we tried this out on the Mijoko swimmer example. We only generated about 1 to 5 rollouts from a trained expert policy. We learned the dynamics using the contraction-based losses and neural networks. And then we performed simple policy optimization using finite differencing, which is the ARS algorithm. And what we can see here is the task cost performance. So as we increase the number of training steps, what we can see is that when we optimize for performance using the composite loss with the contractively regularized learned dynamics model, we achieve faster convergence to an optimal policy as compared to models that were using just L2 regularization, or just models that only optimize for your task performance, but have no notion of trying to track stable expert trajectories. So the takeaway from the first part of this talk is that the notion of stabilizability can act as an impressive regularizer for learning dynamics, especially when learning from smaller data sets. And so obviously there's the disconnect between what I proposed initially, where I want to encode stabilizability as a constraint, and then gradually relax that to a form of regularization by using sampling. Despite that fact, we can still observe great advantages in the sample efficiency of the learned policies. So before I go to part 2, I just want to pause here for some questions. Okay, everyone understands contraction.
There is a question.
So the second part of the talk.
Can you hear me, Sumeet?
There's a question. Yes. Yep.
Hello?
Yeah, Amon, you can unmute yourself and talk. Yes.
Yes, I had one question regarding the learning of from expert trajectories. How do you know if such a trajectory is stable, like in the CCM sense, if it's like a finite time trajectory? I'm not an expert on this notion of stability, so
sure.
I was interested in that.
Yeah, so standard Lyapunov stability just says that your trajectory should be bounded, right? Contractive stability, it essentially just says any pair of trajectories should be converging to each other. So if I give you a demonstration data set where none of the trajectories explode, we know for sure that they're at least Lyapunov stable over the finite horizon. And therefore, imposing the fact that nearby trajectories are also stable with respect to each other is actually a natural follow-on conclusion. So it more closely resembles, another way to think about it is that what we really care about is not so much stability of an equilibrium point. We really care about stability between pairs of trajectories. And that's the notion of incremental stability, which is what contraction captures.
Okay, so it's more like not really an asymptotic stability, but rather like a stability in the sense that the distance of the trajectories stays bounded over time.
Correct.
Okay.
So if I consider the set of all demonstration trajectories, as long as that's bounded, that basically says that's exactly what incremental stability is trying to capture. Yeah.
Okay, thank you.
Sure. Okay, so we'll go on to part 2. Part 2 is a little smaller because it's still current work in progress, but we have a draft and submission to IROS this year. And the focus of part 2 is on the notion of how to deal with the setting where you have multiple sensors arriving at multiple frequencies into your policy, and you need to make actions in real time, so realize actual continuous time control. So the framework that we will be using to tackle this problem is using Neural Controlled Differential Equations, and I'll introduce the infuser architecture and related experiments and future directions. So the problem setting is as follows. Imagine you have your robot, which is equipped with a range of sensors. So you have RGBD cameras, you have maybe audio inputs coming in as well. This could be, for instance, related to language condition models. You have natural proprioceptive sensor, and then you also have tactile touch feedback as well. And all these things are coming in at vastly different frequencies. So I've put up hypothetical numbers here, but a vision pipeline, for instance, might only be running in the realm of, let's say, tens of hertz, whereas audio signals are in the range of kilohertz, and your touch sensors is in the range of hundreds of hertz. And all this information coming in, and you need to make a decision in real time to try and actually deal with the agility of the problem. So you need to make continuous controlled decisions, taking into account all of these various frequencies of your sensors. So the standard way one might approach how to encode all of these different sensors is to say, okay, everything that's time-based, I can batch into fixed time windows, put them through modality-specific encoders, so things like RNNs, for example, put my RGBD and anything vision-related through standard CNN or vision-based pipelines, and everything feeds into a shared latent space. Now, this latent space itself can be trained either using self-supervision, so using essentially auxiliary losses. So that's how you train your latent space, and then you fix that latent encoding, and then use the downstream encoding to essentially as your policy architecture. So that's one common approach. Or you can just append the policy MLP architecture to this latent space and train this end-to-end conditioned on the task. And while this kind of a structure preserves the MDP aspect of the nature of the problem, what really, I think what we should really pay attention to the fact is that this is really not an MDP. You can think about the images, for instance, coming in at discrete time indices, indexed by a little t here. But everything else that's coming in at higher frequencies is really an approximation to a continuous time process. So the way we should be thinking about observations here is that x of t is an observation function. It's a map from a time domain, limited time domain from 0 to t. You can think of this as spanning the time between two successive images. It's a map from that time domain to the space of signals. And x of t, for instance, can include all of the remaining sensors that are at higher frequency, let's say, than your images. So the fact that this is really an approximation of a continuous time process, and we need means that we need to be able to react in continuous time. We need a continuous time reactive control policy. Mathematically, what this means is that we need a functional transform to go from this observation function to a control function. A policy outputs a function as well. So the question is, how do we actually parameterize these functional maps in an efficient way? A very natural way to do this, which has been very popular in robotics for several decades now, is using dynamic movement primitives. So I've cited an extensive review here, and this essentially lays out the fundamentals of DMPs. These are a class of stable second-order models, for instance, that encode things like the motion of your end effector. The kinds of these models can capture various properties, things like attraction to a goal point, rhythmic motions. You can define these second-order models on general manifolds, so rotation spaces, Quaternion spaces. You can augment these second-order models with sensor modulation to try and account for things like collision avoidance, shape modulation. This is really a well-developed class of policies. And therefore, it lends itself very naturally to hierarchical structures where, let's say, you take your observations and you map from those observations to the parameters of these DMPs. And now you can roll out these DMPs to iteratively generate your control function. However, there are some limitations with this architecture that typically, in order to be able to generalize in your task to various types of, to various parts of your state space domain, you might need a very large class of movement primitives. And so there's been some recent work on combining these types of models with hierarchical techniques where you learn these DMP models in various regions of your task space, and then you try and combine all these policies together. The second limitation of DMP models is that they're typically only looking at a single sensor modality. And more recently, however, there has been work where essentially you learn families of DMPs which combine subsets of different sensors, and then you take all of these different individual policies and try and blend them together for your task. Instead, the approach that we want to take is using the framework of neural controlled differential equations. And this essentially builds upon a very well understood mathematical field of rough analysis. So I'll give an informal introduction to this idea first. You can think about controlled differential equations, CDEs, as a continuous time limit of recurrent neural networks. And essentially what they're doing is they're generalizing the neural ODE framework by now incorporating a multivariate signal as an input to this model. Importantly, and this is really key here, that we do not require alternating between RNN and neural ODE models, kind of like a hybrid mix, to accommodate irregularly sampled series. So if you think about what's coming into your robot at all the different frequencies, some of them might be irregularly sampled. We don't need to worry about the fact that these are coming in at different frequencies, because everything, as you'll see, will get mapped to a function space, and all the subsequent operations live in functional spaces. And there are also some very nice theoretical properties here, in the sense that these CDEs give us a notion of universal representation from the space of functions to the reals. Although the details of this analysis, however, will be out of scope for this talk. So let's introduce mathematically what these CDEs look like. So let's say I give you a sequence of timestamp measurements, x of t, and you can think of these as a collection of all the measurements that don't correspond to your images. And this could be things, your audio, your proprioceptive information, and touch feedback as well. And you just collect this into a set. And now all we're going to do is fit a cubic spline to this data and append it with time. So x bar of t is simply the cubic interpolation. And now we parameterize a matrix valued function, f theta, and define the function zt as the solution of this controlled differential equation. So this term on the right-hand side is actually a matrix vector product between f theta and dx d tau. And the initial condition is parameterized with a separate neural network, which is conditioned only on the initial observation. So the way you should think about this this model is that this kind of looks like an ODE, but this is strictly this is what's really happening here is that you're doing an integral with respect to the process xt. So what you're really computing is a Riemann-Stieltjes integral. The way you would define an output of this process of zt represents your latent state, you can either define an output after integrating this process for a fixed amount of time, or basically projecting the latent state at every intermediate time to generate a functional output, yt of tau. So you can see that any changes in the underlying process xt will affect the overall vector field that governs zt. So local changes in your input process create local changes, continuous changes in your latent state dynamics. And in differential notation, we notate this very similarly to how you would notate stochastic differential equations. And in this case, the terminology that we use is that xt is the driving process and zt, the latent state, is the driven process. So once again, to reinforce why we want to use models of this form, these essentially subsume and strictly generalize neural ODE representations that look like this. So dz d tau equals some function of the latent state and the direct input of your observations. It naturally, as I mentioned, naturally handles irregular sampling as well as partial observability because everything is operating with splines. And the way we're going to apply it to our control problem is to use neural CDEs to evolve a latent embedding, where this embedding is driven by our high frequency sensor streams. So to put this in perspective, this is what a standard baseline might look like in terms of fusing multiple sensing modalities. So here at the top, we have an image encoder, which generates an image latent state. And then every intermediate time, we take our high frequency reading and we fuse this together within a joint fusion encoder, which is essentially combining the image embedding as well as all your other observations. And then this internal intermediate embedding is then decoded as part of your control function, which is what is generating ut of tau. So as we sweep through tau, going from 0 to 1, we're sweeping through a function, we're generating explicitly a function of values, ut of tau. This is what a standard baseline architecture might look like. How we modify this with CDEs is as follows. We keep the image encoding identical. And now we only look at the initial condition of a high frequency stream to generate an initial condition of a latent state. And now using this initial condition, as well as the functional representation of the high frequency stream, we can evolve the latent state using the CDE. So this is a self-sustaining feedback architecture. And at every intermediate time tau, we can take its intermediate value, ZOT of tau, and decode this to generate our control function. So the natural idea here is that we're creating an implicit functional map from the observation function to the control function, and with the hope that the CD essentially captures the higher fidelity environment dynamics. And you can see, therefore, that this generalizes all kinds of deep dynamic movement primitive models as well. Are there any questions about this architecture before I move on to some results? Okay. So we tested this out on some imitation learning examples. Specifically, we just tried the simplest possible imitation learning algorithm, behavioral cloning, where the expert policies were pre-trained with privileged information. And we also compared it to two additional baselines. One is essentially taking the baseline architecture, and instead of feeding in the raw value of X, we feed in a moving average filter. And then the second algorithm that we compare to is a recent state-of-the-art algorithm, which essentially takes your image and the most recent high frequency reading and converts it to the set of parameters of a DMP. And this DMP is now then rolled out open loop until you see the next image observation. And then we perform two forms of evaluation, which are somewhat unusual for behavior cloning. The first one is throttling, where we try and increase the duration between successive images. So here we're really seeing how much can we get away with decreasing the image frequency rate, the video rate of our robot, and still maintain agile control and accomplish the task. And the second form of evaluation is where we can randomly drop images with some probability. So can our model actually cope with using stale images, but still using this internal latent representation that's being evolved with time, and still use that representation to generate agile control actions? We tested this out on two classes of systems. One is arguably what you might call a quasi-static task. So this is the task at the bottom, which is essentially to just take a piece of cloth and drape it over an object. And so here, our high frequency readings are just the robot proprioception and velocities and the gripper status. And a control action is just the end effector displacement and the gripper command. And then we also compare these policies on a much more agile task, which is a standard ball and cup example, but sort of atypical of the standard ball and cup example. We allow the mass of the object to vary as well as the max length of the elastic string. And instead of using joint information or position information about the cup, we only allow ourselves to use the force torque sensor co-located with the cup position. So I'll present results on cloth covering first. We have two metrics. The first metric on the left-hand side is the max reward. And in this case, in the cloth covering, the reward is basically how much of the object have you covered as a ratio from 0 to 1. And on the right-hand side is the total reward. So the total reward really captures how quickly you're accomplishing the task. And therefore, it's a measure somewhat of efficiency. So as expected, what we see in the quasi-static task is that all the models somewhat perform on par. And this basically says that these models are not overly sensitive to the high frequency sensor readings, meaning I can observe a single image and then roll out a vast number of actions, in this case, up to 30 actions without seeing a next image and still be able to accomplish the task. When we start to drop images, we start to see some degradation in the open loop policies, which is what the NDP policy is. But we see, again, fairly good consistency in all the other closed loop policies, which again show a very limited sensitivity to the possibility of dropped images. However, when we go to a more agile task, so the ball and cup example, this is where we start to see real advantages of the CDE framework, where as we increase the duration between successive images, we see that the CDE model's performance degrades quite naturally, whereas all the other models start to degrade quite rapidly. And this is achieved in both metrics, so the max reward, as well as the efficiency metric on the right-hand side, the total reward as well. And what this essentially suggests is that the CDE model is a better representation for creating functions, for creating functional maps, so mapping from the observation function to a control function for dynamic agile tasks. So some of the ways, and then also obviously in the drop, we see similar performance where we see a natural degradation of all policies, but we see the highest performance coming from the CDE infuser model. So what this essentially suggests is that the CDE model is well conditioned for agile tasks, and therefore this is the current future direction that we're proposing to actually to implement these algorithms on the set of tasks which are fundamentally bottlenecked by vision. Some other ways that we're also exploring on how to expand these is to how to incorporate stochasticity and multimodality in these functional representations. So I think I have a few 5 minutes left. I just want to close this talk with a discussion of how I sort of see all of these techniques going towards sort of how we want to view the future of the robotic autonomy stack. So how do we connect specifically all these different techniques that we have for doing lower level control with the higher level planning, where higher level planning really constitutes direct interaction with a human agent? So as I mentioned at the beginning of the talk, we have some incredible results with language models, which basically show that you can combine the output ranking of language models with the value functions of policies to try and figure out what is the ranking of subtasks that you should follow to try and accomplish a given overall task given to you by a human. So if we think about essentially how this robot stack, I think you can generalize as a robot stack, how this is really working is that you have a large language model that's breaking down your task into a sequence of subtasks. You have a bank of policies, in this case, a set of deep RL policies that are providing feedback in terms of their value functions based on the current observations. So in the SECANT paper, this is known as affordance. You can think of this as sort of the probability of success of each of these subtask policies. However, where I really want to see progress being made going forward is to see how can we extract more meaningful conditioning variables from these subtask representations. An example, for example, would be, can we extract things such as goal positions or constraint functions, general motion variables, cost functions, and I believe Jeanette presented a paper last week on extracting nerf encodings. And I think these kinds of representations are going to be key for enabling other kinds of policies. So things such as model predictive control, and there's some great work from Marc Toussaint's group on sequence of constraints. The infuser architecture, again, conditioned on these kinds of motion variables and constraint functions, gross primitives, and all these kinds of policies and these kind of conditioning variables is where I believe the control theoretic structures really lie. So going forward, I think this is really the most exciting area of research for me, is to how to connect large language models with these special kind of subtask conditioning variables to enable control theoretic policy architectures. So with that, I will close this talk and just want to thank all of my collaborators on these two works. Thank you.
Thank you, Sumeet, for the great talk. Let's open the stage for questions. If you have a question, simply raise your hand, and then I will give you the word, or write in the chat if you don't want to speak.
I'll just switch over here.
Sumeet, okay, so I can start. Sumeet, very, very nice talk. Very interesting. Now, something that really, I was impressed by is this idea that you can, from a natural language, description of a problem, you can come up with a sequence of tasks and decompose it and actually execute them. Now, I was wondering, what do you need for that? Do you need some kind of description of what the world looks like, or this is something that is completely out of context? Just look at the natural language and come up with the task.
Yeah, it's a good question. So the language model has no idea what the scene looks like. So there is some work ongoing on how do you actually tell the language model what is in your scene right now? So let's say a collection of objects on the table. The language model then is only used to say, in a given situation, let's say I spilled my can. It generates a set of candidate responses, or in this case, what they do is to feed it a set of candidate responses, which corresponds to various subtask policies. And the language model essentially outputs a set of probabilities for these subtasks. So let's say if the example is get me an apple, then the various subtasks that are fed into the model are, okay, search for an apple, go to the apple, pick it up, and return it to me. So the language model is only tasked with ranking which of these things is most relevant for the given task, irrespective of what is in the scene. This has to be combined with something that's taking in environment information, so things like images and the current state of the world, which tells you which of these subtask policies is actually feasible and achievable at the current time. And then in the SECANT paper, they just do a cross product. So it's just a multiplication of the ranking from the language model with the ranking from your affordances or your value functions. And this basically gives you a rough ranking of which subtask to tackle next. So the language model by itself, of course, cannot be used in isolation. It has to be given some help with a second model, which is giving it information about the environment.
Right, because for example, look at the case where you spill your coffee, right? So the appropriate action could be different if you are at home, right? So maybe, okay, so you want to, get a towel or something, and
yeah.
But maybe you are at the beach, right? So you spill your coffee, then, well, who cares? Just get another one, right? So,
right.
So, and then, the way to intervene may depend on what else is around, right? So if you have some, paper towels or something, it's one thing, right? It's if you don't, it's different, right? So, yeah.
Yeah. So actually, I have a colleague. I think he's on this call. He might still be on this call, Andy, who's actually working on what he describes as Socratic models, where the idea is to combine different kinds of models. So models trained on language or models trained on audio, visual inputs, and essentially have these models talk between each other. And so this could be a hypothetical way to essentially condense information. Maybe one model is providing you the visual feedback about what everything that is in your surroundings. Another model might be listening to the audio signals in your environment and trying to, again, summarize information. And the connective language, the connective way to communicate between these models is natural language. And so as you just keep passing information between these different kinds of models, you can come to a consensus as to, well, what is the state of my world? What is the state of my environment? And then maybe you go down to this model, which says, okay, now figure out a set of appropriate subtasks for my policy.
Okay, that's very interesting, right? So essentially you're saying the natural language could be the connective tissue in a sense, it could be the interface, right? Is that what you're saying?
Yeah. I think that's actually a direct quote from Andy, one of Andy's presentations and papers.
Wow, I mean, that's actually very interesting. But does it have to be natural language, or you can think of something a little bit more abstract? I'm just thinking of like a Chomsky, like a universal grammar kind of thing, right? So,
right, yeah.
In a sense, could be easier, to use a natural language, use it easier for the user, right? But for the machines, maybe something is a bit more abstract could be.
Yeah. I think there's a, sorry, I'm in a conference room, so, but I think there's definitely the possibility. It doesn't necessarily have to be natural language. The fact that some of these models can actually output code suggests that they can in fact think and reason in terms of code and variable constructions and everything. So I think there's definitely a lot of open space to figure out what is the correct grammar to communicate with the robot. But at least on the understanding interface side of things, on the human interface side of things, I think natural language makes sense there. And then how you condense that down to communication with a robot, you have a lot of flexibility. But I still think there's a lot of open research there on how do you convert these subtasks into a sufficient resolution that actually makes sense, that, okay, now I can pass it off to a low-level control algorithm.
Right. Yeah, that is very fascinating. Yeah, I agree. Yeah. Thank you.
Okay, sorry, I definitely have to go in the conference room. Thank you so much once again for the invitation.
Thank you, Sumeet, and good luck for the next steps.
Thank you, Sumeet.